Today, we are going to take a look at small modular nuclear reactors, or SMRs. We will explore the technology, history, and industry of SMRs. What are small modular reactors? How are they different from traditional nuclear plants? How does this relate to renewable energies? Why should anyone care about the company X Energy? My name is Alex Kaiser, and over the next few minutes, I will attempt to answer these questions. So sit back, relax, and throw some enriched uranium particles in the microwave, or rather, don't. First things first, what is a small modular reactor, or SMR? An SMR is like a traditional nuclear power plant in that it utilizes nuclear fission to heat up a gas in order to spin a turbine and produce electricity. A quick breakdown of fission. When the bond that holds protons and neutrons together is broken, a tremendous amount of energy is released. Nuclear reactors break down these bonds by shooting neutrons at heavy atoms like uranium, which in turn release more neutrons, which break more bonds, and so on. This process releases an incredible amount of thermal energy, which can be harnessed. This thermal energy heats water into steam, which spins a turbine, which generates electricity. So, SMRs and conventional nuclear reactors both use nuclear fission to create electricity, but how are they different? For starters, they're much smaller. SMRs require only a fraction of the land needed for a conventional plant. SMRs need about 65 acres compared to the nearly 3,000 needed by typical power plants. Also, they're modular, meaning they can be built in one location and transported to where they will be deployed. This is a huge advantage over conventional plants. It saves a lot of time and money to produce reactors in a central location and then distribute them to where you need the power. Conventional reactors can take decades of planning and construction before they are operational. SMRs have smaller electric production capacities than conventional reactors, typically anywhere from 60 to 300 megawatts, compared to the roughly 1,000 megawatts of a conventional reactor. However, because of their design, SMRs can be coupled together easily and scaled up. X Energy is planning to deploy 12 reactors in Washington state for a total of 960 megawatts of electric production. To further explore the differences between SMRs and conventional nuclear reactors, we'll take a quick history lesson. The first reactors, now known as Gen 1 reactors, were developed in France in the 50s and 60s. They used natural uranium and are now obsolete. In the 60s and 70s, the United States and Russia developed and deployed a number of different nuclear reactor designs. These are called Gen 2 reactors and account for 2/3 of reactors in use today. They use fission to heat water into steam and turn a turbine to create electricity. They also typically use boron, a very boring element, to control the reaction. When engineers want the reactor to stop or slow down, they insert rods made of boron into the reactor to cool the reaction. The reactor housed in the engineering building at UW-Madison, the Chernobyl reactor that exploded, and the 3 Mile Island reactor in Pennsylvania that experienced a partial meltdown are all Gen 2 reactors. Gen 2 reactors in nuclear power plants often generate up to 1,000 megawatts of electricity. Gen 3 reactors are very similar to Gen 2, but they use uranium more efficiently and are believed to be safer than Gen 2 reactors. Now, finally, SMRs. SMRs are Gen 4. There are a few Russian models that use Gen 2 or Gen 3 technology, but by and large, SMRs are Gen 4. There are over 80 SMR designs in various stages of development, but a popular one, and the one used by X Energy in its flagship reactor, the XE100, are known as high-temperature gas-cooled reactors. They use coated fuel particles, such as tristructural isotropic particle fuel for their fission, which is not only much safer, but much more efficient than conventional uranium fuel. So far, all HTGRs use helium gas for cooling. Helium is stable and does not become radioactive when exposed to radiation. Let's take a closer look at the fuel. specifically the fuel used by the XE100. Encased in a billiards ball-sized sphere of granite, known as a fuel pebble, are 18,000 tristructural isotropic, or TRISO, particles, each with a microscopic kernel of super-enriched uranium surrounded by 3 indestructible layers of carbon. These layers of carbon contain 99.99% of fission byproduct, i.e., radioactive material. TRISO particle fuel doesn't require a containment protocol because the fuel itself is the containment. More than 200,000 fuel pebbles are cycled through the core of the XE100 like gumballs through a gumball machine. It's designed to operate for 60 years without the need to be refueled. Conventional reactors need to be refueled every 1 to 2 years. How do SMRs fit into the discussion on renewable energy? First, they are a zero-emission form of electricity production. Second, unlike solar and wind, they have a consistent power output and can be scaled up or down as the grid demands. Third, SMRs use a fraction of the water of most forms of electricity production. Fourth, there's a lot of power in nuclear energy. Nuclear could be the backbone of the grid, readily replacing coal and natural gas, while greener energy sources continue being researched. SMRs are ideal candidates to directly replace coal in existing power plants. Because of their size and transportability, a power company could refigure their plant to be powered by an SMR for a fraction of the cost of developing a new plant. Further, there is a classification of SMRs known as microreactors. These are reactors that have a power output of anywhere from 1 to 20 megawatts of electricity. What are they good for? Well, a lot actually. 5 to 10 megawatts of power is enough to power a small city or town. Imagine if the thousands of rural communities in the US didn't need electricity from a power plant hundreds of miles away, and instead could be powered by a local microreactor. Also, factories that need a lot of electricity could ostensibly be powered by one microreactor for years, rather than draw huge amounts of power from coal or gas power plants. Microreactors could also be used on huge shipping vessels, which use an insane amount of petroleum to move goods across the oceans. The military is already using Gen 2 reactors in most of its aircraft carriers and nuclear submarines. Why not bring safer and more efficient reactor models to the commercial realm? Lastly, there's one more specific thing that SMRs can do to help lower emissions and get us away from fossil fuels. Keen listeners will remember that the XE100 is known as a high-temperature reactor. What does that mean? Well, certain industrial chemical processes, like the production of steel, glass, cement, or ammonia, require a high amount of heat. Most chemical reactors use natural gas to accomplish this. So while electricity production is important to achieve zero carbon emissions, we also need to find out how to get things really hot without using fossil fuels. Enter the XE100. It can withstand temperatures up to 750 degrees Celsius, meaning an operator can allow it to get very hot and then use that heat in chemical processes. X-Energy was founded in 2009, but sprang into relevancy in 2016 when it was awarded a $40 million grant by the Department of Energy to participate in its Advanced Reactor Demonstration Program. Since 2016, X-Energy has received hundreds of millions of dollars more to continue research and development of advanced nuclear reactors. In 2019, Clay Sell, a former Deputy Secretary of Energy under the George Bush administration, was appointed X-Energy's CEO. In 2022, X-Energy began construction on an enriched uranium manufacturing plant in Tennessee. In 2023, they partnered with Dow Corporation and selected a site in Texas for deployment of their first small modular nuclear reactor, the XE100. They also partnered with Energy Northwest, and chose a site in Washington to build a series of modular reactors that are planned to generate a total of 960 megawatts of electricity. They expect the first reactor to be online by 2030. Furthermore, they received $17 million in funding from the Department of Defense to develop a microreactor, the XE Mobile, to be deployed in remote military bases. X Energy hopes to develop the reactor for use in commercial applications, such as powering factories, small to medium cities, or use in transport reactors, such as the ones found in nuclear submarines and aircraft carriers. Still in 2023, X Energy was selected to develop a nanoreactor for use in spacecraft. A 40-kilowatt design was submitted to the Joint Emergent Technology Supplying On-Orbit Nuclear, or JETSON, program under the Air Force Research Laboratory. In October of 2024, X Energy announced a large investment from Amazon, who committed to paying for the first 4 reactors being built in Washington state. Suffice to say, X Energy has had a staggeringly busy couple of years, and with the modular reactor industry predicted to explode in the next 7 years, climbing from a market share of $3.5 billion in 2020 to a projected $16 billion in 2030, it's safe to say they have a busy few years ahead of them as well. In conclusion, the future of nuclear power is bright and continues to grow. Companies like X Energy are blazing the trail of safer and more efficient methods of nuclear power production. In order to achieve emission-free electricity, it is imperative to pursue nuclear energy. Small modular reactors like the XE100 promise a safe, clean, and efficient form of energy. I, for one, am thrilled about the future of nuclear power in the US, and I hope you are too.